We first started off networks with DC circuits, right? Direct current. And then we discussed about alternating current. Okay. So whatever we discussed in alternating current, that is relating to the single phase. Okay. So that means there is only a single AC source. Now we are going to discuss about three-phase systems. Okay. In three-phase system, what happens? You have three AC sources which are going to have a mutual phase shift of 120 degrees. So that means if one phasor is going to have a 0 degrees reference, right? Then the other phasor is going to be 120 degrees lagging. Another phasor is going to be 120 degrees. So you can see that each of the phasors, they have a phase shift of 120 degrees. Okay, so such a system is called a three-phase system. What is the phase shift? This is single phase, three phase. What about two phase? Why are we not discussing about two phase circuits? So in two phase, we call a two phase system when there is a phase shift of 90 degrees. Okay, 90 degrees phase shift. Now why we are preferring the three phase system is that it has a certain advantages. So what are those advantages? Advantages of three-phase system. The very first advantage is that the power, the instantaneous power is constant. So we have seen in a single phase system, the power had an average value and a pulsating component as well. Okay. But in case of three-phase system, the instantaneous power value is going to be constant. So we will discuss the derivation later. The second point is, for the same amount of power, the three-phase system is more economical. So the reason for this is that the volume of the wire required, we have conducting wires, right? So the volume of the wire required for the same power is going to be lesser in a three-phase system. Okay. So because volume of conducting wire wheel, right? Conducting wire is lesser. So these are the major two advantages because of which we prefer the three-phase systems. Now three-phase systems, they can be connected in two different configurations. One is the star configuration and other is the delta configuration. So what happens in a star configuration? You will have three phases, and these three phases are going to be connected to a single point, common point. And from here, the power will be delivered. So these are the power lines. And this common point here, we call it as the neutral point. So we denote it as N. And the three power lines, we can take it as A, B, C, or it is also represented as R, Y, and B. Okay. Now what happens in a delta configuration? Here it is going to be slightly different. These are the three sources. So these are going to be connected like this. You can see that there is a sort of a triangle formulation here. And the lines, the power lines are going to be derived like this. Okay. So what are the power lines? Once again, they will be represented as A, B, C, or they can be represented as R, Y, B. Okay. So now each of these three phases, they will have a phase difference of how much? 120 degrees. That means if this is 0 degrees, this is going to be minus 120 degrees, and this is going to be plus 120 degrees. Similarly here, there is going to be 0 degrees, 120 degrees and 120 degrees, minus 120 and plus 120. At this point, we can understand what is a balanced system. See, sometimes the phases won't be exactly 120 degrees out of phase. Okay. So that is why we define something called as a balanced system. So you can take it like an ideal three-phase system. Okay. So what are the conditions for a system to be called as a balanced system? The only condition is that the sum of all phasors, all three phasors should be 0. Okay. So that means if you take the phase A as VA, phase B voltage as VB bar, and phase C voltage VC bar, then if you add all three of them, then you're going to get 0. Okay. So this is what makes a balanced system. Now for this to be 0, when all of the phasors, if they are added, it should be 0. When will this occur? This will occur when there is magnitudes, equal magnitudes are equal, and the phase condition is that each of the phases should be having a phase shift of 120 degrees. Okay. So phase shift or phase difference between the three phases should be 120 degrees. Okay. So this is what is called as a balanced three-phase system. And the next point you need to understand is the phase sequence. Okay. So that means we saw that each of the phasors, they are 120 degrees out of phase with respect to each other. Now if this phase is A and this phase is B and this phase is C, then the phase sequence we call it as A, B, C. Okay. So why we set a phase sequence? This will give us an information about which phasor is 120 degrees lagging or which phasor is 120 degrees leading. Okay. So if A, B, C is given, that means usually we take A as the 0 degrees or whatever the angle. Let us say phi we take. Okay. So it is phi, let us say. Then this means that B will be lagging A by 120 degrees. So that means phi minus 120 degrees. Okay. And finally C is going to be phi minus another 120 degrees lagging. That means lagging B by 120 degrees. So you can either write it as phi minus 240 or minus 240 is nothing but plus 120. So you're going to write phi plus 120 degrees. Okay. So the phase sequence will give you an idea about which one is lagging, which one is leading. Okay. So what is the other kind of phase sequence? There are only two choices of phase sequence that you will get. Okay. So the other choices A, C and B. So in A, C, B, what is going to happen? If this is phi, then this is going to be phi minus 120 and this is going to be phi plus 120 degrees. Okay. So here don't think that only A is starting. What about if B starts? Maybe that will be a different sequence. That is not the case. It is just the order. See, after A, B comes, after B, C comes, and after C again A comes. Okay. So whatever way in which you write it, A, B, C or B, C, A or C, A, B, it is going to be the same phase sequence only. Okay. So you can better understand it if you draw the waveforms. Okay. So the first A, let us say phase A, it will be like this. Okay. We will start from here. Now the second, this we will write as A. Now the second phase is for ABC sequence, let us say. The second phase is B. Now B will be starting 120 degrees after A starts. Okay. So 120 degrees is going to be somewhere here. So from here the 0 will start. Okay. So this is how it is going to be. So if this is 2 pi, right, this will be 2 pi. So this will be 2 pi plus 120 degrees. Then after that, where will C start? C will start, you can either consider it to be taking after 120 degrees after B. This is B. Or you can also consider it as starting from 120 degrees ahead of A. Okay. Both are going to be the same thing. This is 120 degrees after B, and this if you take to be 120 degrees ahead of A. So you're going to get here it will start and again here it will end. Okay, because the next cycle it will again start like this. Okay, so in this manner you can see that you can mark this as C. So you can see that if you are starting from A, then here A is starting, B is starting after 120 degrees and C is starting after 120 degrees. If you start from C, then A is lagging C by 120 degrees and again B is lagging A by 120 degrees. Okay. So this is how the waveforms will be for a three-phase balanced system. You can see that the magnitude are also all equal. Okay. So these are all equal magnitudes Vm. So these are some of the base concepts in three-phase systems. Next we will see the phase values and line values. So what is meant by phase value? What is meant by line value? If you're talking about a phase voltage, then it generally means that the voltage that is existing across the particular phase. And if you're talking about a line voltage, then there are three lines in three-phase system, right? So the line voltage will be the voltage between two lines. And what about phase current? Phase current, again you will have to consider each. See, here I am expressing in terms of an impedance value or a circuit element. You can take it as a source as well. Okay. So this represents a circuit element. It can be a active element or a passive element. So now what is the phase current? The current that flows through each phase. And what about line current? The line current is the current that flows through the line. Okay. So we will see for star and delta configuration once we take, you will be able to differentiate between what is a phase value and what is a line value. Okay. So first we will start with the star configuration or the Y configuration. So it is referred in both the ways. So you need to know that both the names represent the same connection. Okay. So like I told you, the star configuration is going to have a neutral point and all of the sources, they meet at the neutral point. Okay. So this is phase A, let us say. This is phase B and this is phase C. And here we can take as the neutral point. For a balanced system, there is not going to be any current in the neutral. Okay. So why is that also we will understand shortly. So what will be the phase currents now? The phase currents will be the current through each of the phases, right? So this is one phase. This is the second phase. This is the third phase. So here you have the current you can write as I phase. And this current corresponds to the phase A. Here also I phase only, but it corresponds to phase B. So it will have a different phase value. Similarly, this is also I phase, but it will correspond to phase C. Okay. Then what about the phase voltage? The phase voltage will be across this phase. That means what? Across A and N. So this is going to be the phase voltage and we can express this as VAN. Similarly, the voltage across this phase is going to be VBN. And what about C phase? This is going to be the voltage VCN. So these are all the phase values. So always the line will be the positive polarity, neutral will be the negative polarity. Okay, because the positive polarity of the source is going to be towards the line. What do we mean by positive polarity in an alternating circuit? It just means that the positive half cycle, we consider it to be this to be the positive terminal during the positive half cycle. Okay. So we have discussed the phase currents and the phase voltages. Now what about the line currents? When we are talking about line currents, we are concerned with the lines. So first we will see what is the line voltage and then we will see what is the line current. Okay. So like I said, line voltage is going to be the voltage between the lines. So we don't have to care about the neutral wire. Okay. So what will be the voltage across these both lines is going to be VAB for ABC sequence. So whenever nothing is mentioned, we usually consider it to be ABC sequence. Okay. Or RYB. These are some standard sequences. So this is VAB voltage. Next what we have? VBC. The voltage between B and C terminals will be VBC. Next VCA will be the next voltage. Okay. So these are the line voltages. So here you can see that VAB we can express in terms of the phase voltages. How you can express? Here VAB is equal to VAN plus VNB. VAB is equal to VAN plus VNB. Okay, but this you can write as VAN minus VBN. Okay, so that means when you are taking from N to B, you have V and B. If you want to reverse the polarity, then you just put a negative sign. Okay, so minus VBN. So that is why we write as VAB. Similarly, you can write for other phasors as well. What is VBC? This is VBN minus VCN. VCA is equal to VCN minus VAN. Okay, so these relations we will be using when we draw the phasor diagram. Okay, we will draw the phasor diagram. So next, the line current. So the line currents will be the current flowing through the phases. So the line current of A phase will be IA, B phase will be IB, and this will be IC. So these are all the line currents. Okay, and these are the line voltages. Now here you can see that the phase current is equal to the line current. Okay, so in a star configuration, the relation between the voltages is given like this, and the relation between the currents is going to be IL is equal to I phase. So now we will draw the phasor diagram. So we will start with the phase voltages. Because we have the voltage sources here, we can take that the voltage sources are generating voltage with the required phase shift. Okay, so we can take this to be the reference values. So this is going to be VAN. What is this? It is a phase voltage. Then VBN, it will be generated 120 degrees lagging to VAN. Then what about VCN? This is going to be further lagging the VBN voltage. So these are the phase voltages. Now we want to express the line voltages. Okay, so VAB is VAN minus VBN, right? So this is VAN you have, VBN is here. Now minus VBN will be opposite, 180 degrees opposite. So that means this is going to be minus VBN. Okay, now if you add these both phasors, then you are going to get VAB. So this you can do by the parallelogram law of addition. So this is going to be VAB. And what will be this angle? See, this is 120 degrees, right? This is 120 degrees. Now this is a straight line because this is 180 degrees. So what will be this line? It is going to be 60 degrees. Now the diagonal for a parallelogram will bisect the angle. So this is going to be 60 by 2, which is 30 degrees. So you can see that in a star connection, the line voltage will lead the phase voltage by 30 degrees. So this is the phase relation. What about the magnitude relation? Magnitude is going to come VL is equal to root 3 times the phase value. So how to get this? If you take the example of VAB, so this is VAN minus VBN, right? So how you can write VAN? It will have the phase value magnitude V phase if you take angle 0 degrees minus VBN will be V phase angle minus 120 degrees. Okay. So this if you simplify, you're going to get root 3 times V phase angle 30 degrees. So you can see that the magnitude is root 3 times the magnitude of the phase. Okay. And it is leading by 30 degrees. So this is VAB. What about other line voltages? VAB is lagging VAN by 30 degrees. So VBC will also be lagging VBN by 30 degrees. Similarly, VCA is going to lead VCN by 30 degrees. So what are the important conclusions here? For a star configuration or a Y configuration, you have the line voltage VL is equal to root 3 times the phase voltage. This is the magnitude condition. And the phase condition is that the line voltage will lead the phase voltage by how much? 30 degrees. What about the relationship between currents? The line current is equal to the phase current. Okay. And one more thing that you can see here is, this is a node, right? This is the neutral node. Now you can apply KCL here. So if this current is IA, this is IB, and this is IC. Now IN, if you take to be the neutral current, then what will happen? IA plus IB plus IC plus IN all should be equal to 0. But we know that for a balanced system, the sum of the phasors will be equal to 0. Okay. So that means you can write IA plus IB plus IC plus IN is equal to 0. This is by KCL. So this implies that IN is equal to 0 since the sum of phasors for a balanced system is equal to 0. Okay. So that means for a balanced system, we don't need a return path. We don't need the neutral. If no current is flowing through the neutral, then do we need the neutral line? We don't need it. Okay. So for a balanced star configuration, therefore for a balanced star configuration, neutral is not required. Okay. So if you remember, I told you that the three-phase system is more economical. That is because there are only 3 lines we need. Okay. All the 3 line currents. That is enough. Neutral is not required. So this is a saving of the conductor volume. Right. Now till now we have talked about sources only. Right. So that means here when you took the star configuration, we had sources. Similarly, we will have loads as well. Okay. So how will a 3-phase load look like? Load means there will be impedance values. So this is going to be the impedance. Okay. So this we take as A, this we take as B, and this we take as C. So why are we not randomly taking this as B and this as C? Okay. Because we are just trying to ensure that, see, this is A. If this is A, then B should be lagging by 120 degrees and C should be leading A by 120 degrees. Okay. So just to get this uniformity, we draw like this. But instead, if you take the terminals on the opposite side, so that means you are taking like this, then you can write as A, B and C. Okay. So this is a kind of notation that some textbooks might follow. So I am just explaining it to you so that you will understand why we are exchanging the terminals in this manner. Okay. So in the source case, we have taken the terminals on this side. So that is why we did not have to invert it. And also sometimes what happens, you will have another way of representing this. This is how you draw the configuration, the star configuration. In this way, if you take this as A, then you take this as B and this as C. Now, when do we call a 3-phase load as a balanced load? We call it as a 3-phase balanced load if each of the impedances are equal. Okay. So that means if ZA is equal to ZB is equal to ZC, magnitude as well as phase we are talking about, then this will become a balanced load. Okay. Now we will discuss the delta configuration. So in delta, you are going to have the connection like this. Right. So if you take this as the A terminal, then this you can take as B and this you can take as C. Now what will be the phase voltage? The voltage across this. So you can write this to be V phase. Now you can also see that the line voltage is also the voltage between the lines, right? So that means in a delta configuration, V phase is equal to V line. Okay. So this positive terminal we write here as VAB, and this is going to be VBC, and this is going to be VCA. Okay. Next, what about the phase current? The phase current is simple. It is the current flowing through the phase. Okay. So this we will take to be flowing out of the positive polarity. So this is I phase. Similarly, you have the phase current here. Now what about line current? Line current is the current flowing through the lines. This is IL. So you can see that here the phase current is not equal to the line current in the delta configuration. Okay. So how do we name these? This current, this line current we write as IA, this as IB, and this as IC. And the phase currents we will name as IAB. So we are naming it IAB because the voltage here is VAB, right? So we want the current to also have the same subscript. And here what will be the current? This is going to be IBC, and this is going to be ICA. Now if you apply the KCL at each node, then you're going to get a relationship between the phase currents and the line currents and the phase currents. So we will apply for one equation. If you apply at this node, at node A, then what will you get? IL is flowing out of the node, ICA is also flowing out of the node, but IAB is flowing into the node. So what will be the line current IA? This is IA, right? IA is equal to IAB minus ICA. Similarly, you will get for IB, you're going to get IBC minus ICA. IC, you're going to get ICA minus IAB. So the line current is the current through the line, and I phase is the current through each phase. We will now see what is the magnitude and the phase relationship between the line current and the phase current. So how will we get it? Using the phasor diagram. So in order to draw the phasor diagram, we will take IAB as the reference phasor. So what will be IAB? This will have the magnitude I phase and angle will be 0 degrees. Then what about IBC? This is going to be lagging IAB by 120 degrees. And next ICA. This is going to be further lagging IBC by 120 degrees. Now how will you find the line current? You have here the equation IA is equal to IAB minus ICA. So IAB is here, ICA is here. So we want minus ICA. So minus ICA is going to be diametrically opposite. Okay. So now we can find IA using the vector laws of addition. So you are going to get the line current like this. This is IA. Okay. So with the similar explanation, just like in the previous star configuration, this angle you are going to get 30 degrees. You can verify. This is going to be 30 degrees. Okay. So you can see here that the line current in the case of a delta configuration is going to lag the phase current by 30 degrees. In a star configuration, what did we see? We saw that the line voltage, there it is voltage, and it was leading. Here it is lagging. It was leading by 30 degrees. Here the line current is lagging by 30 degrees. Okay. So these are the few points that you need to remember. But anyways, if you forget also in the case of exam, you can just make a quick phasor diagram. Okay. So now IA is lagging IAB by 30 degrees. Similarly, you will have IB lagging IBC by 30 degrees. And finally, IC lagging ICA by 30 degrees. Okay. So one more thing that you can see here is IA, IB and IC. These are also 120 degrees out of phase, and each of the magnitude will be equal. Okay. So in order to see the magnitude, you can write in terms of the phasors. So what is IA? IAB minus ICA. So what is IAB? I phase angle 0 degrees minus ICA. You can see here this is I phase phase is 120 degrees plus 120 degrees. Okay. So you can write I phase angle 120 degrees. So this, if you calculate, you're going to get root 3 times I phase angle minus 30 degrees. Okay. So here you have the magnitude I line current is equal to root 3 times the phase current value. So in a delta configuration, you can note down the main points. The line current magnitude is equal to root 3 times the phase current magnitude. So line current, if you represent as IL, this is equal to root 3 times I phase. Then what about the phase relationship? The line current will lag the phase current by 30 degrees. So this is the current relationship. What about the voltage? So we saw that the phase voltage is equal to the line voltage. Now, one important operator that you need to know is the operator A. So what is this A? Sometimes you will also see it is being represented as alpha. So what is this? This is a phasor, okay, of magnitude 1 and angle is 120 degrees. Now if you square it, A square, this is going to be what? 1 angle 120 degrees plus 1 angle 120 degrees. So how much is it going to be? 1 angle 240 degrees. But 240 degrees you can also write as what? 1 angle minus 120 degrees. Okay. So now you can represent the three phase in terms of A and A square. So how we can represent? This is the voltage VA, let us take. This is VB and this is VC. Okay. So now VA, if we take as some magnitude V, angle 0 degrees. What will be VB? This will be V angle minus 120 degrees. So what we can write this as? V angle 0 degrees into 1 angle minus 120 degrees. Now what is V angle 0 degrees? It is VA. What is 1 angle minus 120? It is A square. So this you can write as A square VA. Similarly, VC you will get as A into VA. So in this way you will be able to represent each of the phasors in the same variable, that is VA. Okay. So this operator is very useful when you are doing the phasor analysis. Now another relationship with respect to A is, so this is one point. The second point is 1 plus A square you will get as 0. Okay. So why is that? You can get from the phasor itself. What is that? You see VA plus VB plus VC is equal to 0 for a balanced system. Right. So now if you represent VA plus VB we got as A square VA and VC we got as AVA. This is equal to 0. So now VA will be cancelled. So what will you get? 1 plus A square plus A is equal to 0. This is one way of seeing it. Another more simpler way is what? 1 plus A square is equal to 1 angle 0 degrees plus 1 angle 120 degrees plus 1 angle minus 120 degrees. So this, if you simplify, you're going to get 0. Okay. So this is a useful relationship that you can remember. It will simplify some of the processes, some of the calculation processes.